So where is the Avaz? So please make the attendance online. So only a few students are attending today. Okay. So let me share the screen. So let us go through the chapters. What is the important in the chapters? So can you see my screen? Okay. So here we can start with the first chapter that we had here. So I will go through the chapter. So this is the algorithm. What is the definition of algorithm? Then we went through the sort algorithms. Okay. Then this is the well-known computational problems. Okay, this one was the chapter 1, algorithm design strategies, analysis of algorithms. Correctness means give me the right answer. Time efficiency, how much the time and space efficiency. Does there exist a better algorithm? Lower bounds optimality. Okay, what is an algorithm? Here, definition of algorithms. So when we try to define the algorithm, we should go to the finiteness, finiteness, input, output, effectiveness. So why we study algorithm? Because this is the core of computer science. So Euclides algorithm. Here we have an example of problem. We have find the GCD of M and N, the greatest common divisor of two non-negative, not both zero integers M and N. Example GCD 60 24 12, GCD 60 zeros, and GCD here 0. When you have 0, we have to stop. Euclides algorithm is based on repeated application of equality GCD MN. So here this is the GCD example. So how to this is the algorithm of the GCD. Step 1, n while n not equal 0 do. So here this is the n, the number of we have n and m. We have to we want to find the m and n Euclides. So here we have n while n not equal 0, m mod n, a reminder, will be saved at r. Then m equal n equal r, return m. So here this is what we're going to do here is while n not equal 0 do. So here m mod n equal r means the reminder. Then m equal n equal r, and we repeat this when the return m. So other methods of computing GCD: consecutive integer checking algorithm. Here another algorithm of assign m value of m and n to t. Okay. So here, if the divide m by t, if the remainder is 0, go to step 3, otherwise go to step 4. Divide n by t, if the remainder is 0, return to t and stop, otherwise go to step 4. Decrease t by 1 and go to step 2. This is one of the other methods on GCD. This is one that we have. Find the prime factorization of mn, find the prime factorization of n, find all common prime factors, compute the product of all common prime factors, and retain its GCD mn. Why we study algorithm? Here we have theoretical importance and we have practical importance. The main issues related to algorithms, how to design algorithm, how to analyze algorithm efficiency. Okay. Okay, structures, we have the list, array, linked list, string, or stack, or queue, or priority queue, or graph, or tree, or set and dictionary. This is the structure of the data. This is the first chapter that we had here. Okay. So then we move to chapter 2. So in chapter 2, we study fundamentals of algorithms. Here, sorting, searching, graph problems. Here, combinatorial problems like permutation and combination, geometric problem, and numerical problems, or graphs and points. Here you have efficiency, simplicity, and generality. This is the flow chart. We have to solve the steps of algorithm, solving, understand the problem, decide on computation means. This is the flow chart, how to solve an algorithm. Then we go to the design technique of algorithm. Here we have pseudocode and flow chart. And here how to measure the good algorithm, correctness, time efficiency, space efficiency. This is how to measure the effectiveness of how to measure the algorithm. We call it complexity. To benchmark algorithm accuracy for feature improvement, lower bounds optimality. As a mechanism to compare and choose the appropriate algorithm for further implementation. Analysis of algorithm issues, correctness, time efficiency, space efficiency, optimality. Approach, theoretical analysis, empirical analysis. So what is the complexity? We here we say that we do here in our assignments machine dependent and machine independent. The absolute growth depends on the machine compiler used to execute the algorithm and factors. Machine independent, the growth is expressed by the complexity in terms of its relationship to some non-function based on probability, proportionality approach and formally known as asymptotic analysis. Based on the idea that the problem size grows, the complexity will eventually settle down to a simple proportionality to some non-functions. Alhamdulillah. Incorporated in the big O, big omega, big theta. Big O relates to an upper bound on complexity. Big omega relates to a lower bound on complexity. Big theta relates on a big tight bounds on complexity. In mathematical analysis, asymptotic analysis is a method of describing limiting behavior. In computer science, in the analysis of algorithms, it is to estimate the performance of algorithms when applied to very big input data sets. Is a study to the behavior of the point when they are very large. Considering a function fn is when there is a need to describe its properties as n become very large. If n here in power 2, then the function fn is said to be asymptotically equivalent to n power 2 as n go to infinity. In estimating the running time of an algorithm, we may end up the asymptotic behavior as the growth of fn as n gets large. Example, a function fn equal c multiply n power 2 multiply k for some constant factors of c and k. It is said the algorithm to be asymptotically equivalent to n power 2 as n grows to infinity, because we remove the here, because will be negligible according if n is infinity. It is not important to know the constant factors because they would not affect the upper bound or lower and tight bound of running time. Example, n3 power n power 2 plus n. When here n is going of infinity, we don't care about these constants. Order of growth, most important order of growth within a constant multiples as n grow to infinity. Example, how much faster will algorithm run on computer that is twice as fast? How much longer does it take to solve problem of double input size? Here basic asymptotic efficiency classes. So we have here efficiency classes. Here we have asymptotic. We have one constant log n logarithmic, n linear, n log n, n log n power 3 quadratic, and here n power 3 cubic, 2 power n exponential, n factorial, here factorial. So this is the basic asymptotic efficiency classes. So here most of the algorithms goes through these class. Maybe 1 log n, n log n, n power 2, n power 3, 2 power n, n factorial. So here we have quadratic, cubic, exponential, factorial, linear, logarithmic, and constant. Basic asymptotic efficiency classes. Tn equal O1. This is called constant growth. Tn does not grow at all as a function of n. It is constant. For example, array access has these characteristics. The operation AI takes the same number of steps no matter how big A is. Okay. Tn O and log n, this is called logarithmic growth. Tn growth as the base 2 algorithm of n. Actually, the base does not matter. It's just traditional to use base 2 in computer science. For example, binary search has this characteristic. So when we say all log n means most we have the base 2 logarithm. So Tn on, this is called linear growth. Tn growth linear with n. For example, looping over all the elements in a one-dimensional array would be on operation. So here we have constant algorithm, we have logarithmic algorithm, and here we have linear algorithm and examples. So here we have n log n. This is called n log n growth. The n grows as n times the base 2 algorithm of n. For example, heap sort and merge sort have these characteristics. Merge sort, we have n log n. Basic we continue to on power k. This is called polynomial growth. Tn grows as the kth power of n. Selection sort is an example of polynomial growth rate algorithm. It is on power 2. Tn, you have T means n power 2, n power 3, n power 4. This one called polynomial growth. Tn or T power n, 2 power n. This is called exponential growth. Tn grows exponentially. It's exponential big O of T of the n. Exponential growth is the most preferred growth pattern in computer science. Algorithms that grow this way are basically use this or anything for anything but very small problems in computer science. We traditionally use the constant 2, but any other positive constant could be used to express the same idea. So this is the worst complexity. So when n increase, we have exponential growth. So this is the what we call here. This one is what we call one of the most failed growth. So we have with our algorithm we have to take care that to avoid to have these O2 power n. To Tn or n factorial, this is called factorial growth. Tn growth factorial, it is also the most failed growth pattern in computer science. So here also the factorial is also we have to ignore this factorial and 2 power n, because here the growth is really going up when we n is increased. This is here values of some important functions as n go infinity, n when it's 10, here 3.3, n 10 power n, 3.3 times 10, n power 2, 10 power 3, 10 power 3 here for n, here 3.6 times 10 power 6, 10 power 2 here 6.6 here. This is values some approximate of several function importance. So here when we have 10 power 2, if we have here 6.6, okay, 10 power 2 6.6, 10 times 10 power 2, 10 power 4 10.6, 1.3 times 10 power 30, okay, and 9.3 here in factorial times 10 power 157. So here if just for 10 power 2, look here what is the factorial. So here this one we have factorial for 100 number. Last time we try with Ashraf in the class when we try to calculate the factorial, and we noticed that sometimes it give me the message infinity. Okay, this one O1, this one O log n, O n linear, n log n, and O n power 2, O n power 3, O n factorial. Also here will be n 2 power n. Asymptotic analysis, Tn 60 n power 2 plus 5 n plus 1, here 60 n power 2, n power 2. So for 10 here, this is we just use this n when n is 10. We just replace 10 with n with 10. So we will have here 6,051. Here we have 6,000. Here we have 100. If you have 100, so we have 600,000 501. Here 600. Here 10,000. If you have 1,000, you have 60 million, 5,001. And here we have 60 million, here we have 1 million. When we have 10,000, we have here 6 billion, 50,001. And here we have 6 billion. And here we have 100 million. This is just how to make the asymptotic analysis. So here we have n power 2, here 60 n power 2, 60 n power 2 plus 5 plus 1. So this is the graph of this formula. This is asymptotic analysis for this here n power 2, here n 60 n power 2, here 60 n power 2 plus 5n plus 1. Now we have to go to the big O. What is the big O? So we have Gn, OGn, Fn, there is exists positive constants C and N0 such that 0 less than equal Fn and less than equal Cgn. So here we have to be, the Fn should be between 0 and Cgn for all n0. So here we have Fn, we have 0 and Cgn. So the Fn is between. This is the big O, big O. So here Fn, OGn, here we have Cgn and Fn. So Fn, and this is the upper bound, and here we have n. Big O notation defines the upper bound of algorithm. It bounds function only from above. Insertion, sort, worst case O n power 2, best case O n. So here we have n power 2 and O n. This is the algorithm maybe between these two boundaries. Here this is big O. You have big O, big omega, and big theta. Big omega, here omega, here this is what we call it O. Big O. Now here you have omega. Big omega, Gn, Fn, there is a positive constant C and N0 such that 0, Cgn, Fn. So here we have Fn is greater than Cgn is greater than 0. So here we have lower bound. Here we have Cgn, and here we have Fn, and here also we have it is greater than 0. So here we have Cgn. Here for n equal greater than equal 0. So Fn omega n, here we have, so Fn is greater than Cgn. So we have here lower bound. The big O notation defines the lower bound of an algorithm. It bounds function only from below. As we see that here Cgn, the function is Fn, and the Cgn is the lower bound. And this is so best case omega n, omega n is the least used notation. We have big theta, there exists positive constant C1, C2, and N0 such that 0, C1, Gn, Fn, C2, Gn for N0. So big theta, we have a range. So here we have C1G and C2G. So here we have, this is the lower bound, and this is C2Gn is the upper bound. So Fn is between. So the big theta notation defines bounds of function from above and below. So it defines exact asymptotic behavior. Asymptotic order of growth, a way of comparing functions that ignores constant factors and small input sizes. OGN class of function Fn that grows no faster than Gn. Theta Gn class of function Fn that grows at same rate as Gn. Omega n class function Fn that grows at least as fast as Gn. So here same rate, here at least as fast, here no faster than Gn. Because here we have lower bound, here we have upper, here we have upper bound. Gn is upper bound. Here we have lower bound, and here we have between. Okay, here this is big theta between, and here big O. Here we have lower bound, and here we have upper bound. Establishing order of growth using the definition. Definition Fn is in OGN if order of growth of Fn less than equal order of growth of Gn within constant multiple. There exists positive constant C and non-negative integral such that Fn less than oxygen for every n less than greater than or equal to 0. Example, Tn is On power 2, 5n plus 20 is On. So here we have here these examples. Best case, average case, and worst case. That's one we discussed in our assignment. For some algorithm, efficiency depends on form of input. Worst case, see worst n maximum over inputs of size n. Best case, see best minimum over input of size n. Average case, see average over input of size n. So we have worst case, or the worst case, the time complexity, and the best case, okay, and the average case. Number of times the basic operation will be executed on typical input, not the average of worst and best case. The average is not only best between the worst and best. Expected number of basic operations considered as a random variable under some assumption about the probability distribution of all possible inputs. We have sequential search. So sequential search, we have for a given value, we have a key, an array here, and we have array and we have a key. Output the index of the first element of A that match k, or a -1 if there is no matching elements. So this here yi less than n and ai not equal k, do I plus 1. If I less than n, return I, else return -1. So here we'll check all the elements until we while ai not equal the key. So here you check if the one of the element of the array element in the array is equal to k, we will stop and return I if it is less than n. So if we go more than n, means we finish the array, and here we return -1. And the element is not there. So here we want to study the worst case, best case, average case. So here the best case, if we have the item and the is the first element. Worst case, if the key here, best case if the key is the first element. Worst case if the key is the last element or the or not in the array. Average case is between. Empirical analysis of time efficiency. Select a specific typical sample of inputs. Use physical unit of time, example milliseconds, or count actual number of basic operation executions. Analyze the empirical analysis. Okay. One of your friends here start to count the operations, how many swaps, how many comparisons, how many addition, how many multiplication, this kind of empirical analysis. And here we have milliseconds, the time, we read the time, how much it consumes. Okay, machine dependent empirical analysis. Here we have this is algorithm, here machine dependent algorithm, here initial and final screening of typical visualization of sorting algorithm using the bar representation. Here we have, this is the algorithms for empirical analysis. Okay, this is the chapter 2. We go to chapter 3. So here we have analysis of iterative algorithm. So how count to input size running time? Let's assume that I want to follow a simple algorithm instruction. MA0 for I0, I less than n, I plus plus. Here we have 1 plus 1. Here we have 1 plus n plus n. Here we have n. How we find this? Okay, looking up the value of particular element in array, assigning a value to a variable, comparing two values, I less than something until n, increment values I plus 1, assigning value to m until n. This is the here we want to count how many. Here we have 1 plus 1 assign. Here we have assign element, and here we have the we have here 1 plus n, and here we have plus n. Here we have n. Here we repeat this one n times. Here we have comparison n times, and here we have increment n time. Here we compare. Here I equal 0 is 1. I less than equal n. We compare how many times? N times. And we how many times we make addition? N times. That's why we have 1 plus n plus n. Here we have assign 1, and we have to read the 0, a0. So here to find the a0 is the one operation, and here assign the to m is the another operation. So a1 plus 1, and here n equal ai. Here we have n. Here we have n to m, because here we repeat this one n times. Counting an input size of running time, bad idea. So here, counting an input size and running time, bad idea. The number of instructions for this algorithm needed is 3 plus 3n. So here we have plus here 1, 2, 3. Here we have 3 plus 3n. We can define mathematical function fn equal 3 plus 3n. Finally, it ends up with fn 6n. Do we really need to count for every instruction operation? No, we only need to basic operation. So here we want to find for the basic operation the most important operation of the algorithm. So theoretical analysis of time efficiency. Time efficiency is analyzed by determining the number of repetitions of the basic operation as a function of input size. Basic operation, the operation that contributes most towards the running time of the algorithm. So here we have input size, here n. Here we have running time, tn. Execution time for the basic operation, okay, times c, number of times basic operation is executed. Number of times, here number of time basic operation is executed, cn. And here cop, time execution time for basic operation, and how many we call this basic operation executed. Types of formulas for basic operations count. Exact formula Cn equal n times n minus 1 divided by 2. Formula indicating order of growth with specific multiplicative constant. Cn equal to 0.5 n power 2. Formula indicating order of growth with non-multiplicative constant. Cn equal to Cn power 2. Input size and basic operation examples. Problem. Here we have searching for the key. We have number of lists in the time number of list items. Here n. Here what is the basic comparison? Key comparison. Multiplication of two matrices. Here we have matrices. We have matrix division or total number of elements. Multiplication of two numbers. This is the basic operation. What is the basic way of checking primality of a given integer n? N size equal number of digits in binary representation. Here we have division. Typical graph algorithm: vertices and or edges, visiting a vertex or traversing an edge. This is the basic operation of the problem. Iterative vs recursive algorithm. So iteration, here we have non-recursion and recursion and key computer science. Techniques used in creating algorithms and developing software. An iterative function is one that loops to repeat some part of the code, and recursive function is one that's called itself again to repeat the code. Here we have the iterative and the recursion. Already we have go through it. Iteration and recursion are probably best explained using an example of something that can be done using either technique. We find here the factorial. We did this one in our last discussion of assignment. Recursion, it is a problem-solving process. In general, is process where it does or call the same process itself. In particular, a method called invokes itself breaks a problem into identical problems but getting smaller problems. Recursion, recursive algorithm that finds the solution to given a problem by reducing the problem to smaller version of itself, has one or more base cases implemented using recursive methods that calls itself. Base case a recursive division in which the solution is obtained directly stops the recursion. Example, cost of big O. Here we have an sorted in ascending order. Find max integer. Max integer will be max n minus 1. So this is here, let's say of n equal 10, n power 2, n power 3. Here we know to how the time. Here, what is the time? Is here how to find the maximum of n. Maximum integer number of array consists of n number. Example of logarithmic class big O log Tn. Here we have 4i equal I less than n, I equal I power 2 times 2. Print big O O n. So here this is the operation. So here we have to try to find this one. Log to binary log to n. Okay, this is the types of questions in the test. Here, linear class big O. Here we have I less than n, I plus plus, print big O n. Here we have n times. We print this one n times. Here we have log n. So here we have I power 2, so we have log n. Here we have n. Here we have n binary log n if we have two loops. For I equal I less than n, j equal 1 to j less than n, I equal I plus j. Print big O n here log n. Here we have n log n. Example 5, a polynomial class big O n power 2. Here we have I equal I to n, I plus plus. Here this is for like bubble sort and sort. J equal 1, j less than equal n, j plus plus. Print big O. Here we have n power 2. So here we have this one different. That's why we have n log n. But here we have j plus plus. That's why we have n power 2. Here, cube, we have three loops. I less than n, j less than n, k less than n, big O, n power 3. Here we have n power 3. Iterative algorithms. Maximum algorithm consider the problem of finding the value of the largest element in a list of numbers. For simplicity, we assume that the list of is implemented as an array. The following is pseudo code and standard algorithm of solving a problem. Here, maximum element. Here we find to find the maximum element. So here max value equal is 0 for I to 1 to n minus 1. If I greater than max value equal I, retain max value. Here we have iterative algorithm. Here example unique element unique. We have unique. We need to check if this consider element unique problem. Check whether the all elements in a given array or element are distinct. This problem can be solved by the following straightforward algorithm. Unique elements. Here we have determine whether all the elements in a given array are distinct. So no repetition in the element. So here we try to return true if the all elements in A are distinct or false otherwise. Here we have if I is 0 equal n minus 2 do j plus 1 to n minus 1 do. If ai equal aj return false. So here we compare one item with the items in the array. If we have here, look here, we compare with the items. First item with the rest, second item with the rest, third item with the rest. If there is any repetition, we return false. If there is some here, if it is equal, we return false. Otherwise, we return true that the array is uniqueness, means the elements in the array is distinct. Example 9 is sequential search. What is the worst, best, and valid case for the following sequential search? Here we have sequential search, and that we said here, if the item element, the key in the first is the first item, will be the best solution. Worst case, if it is in the end, or the array is not, or the key is not in the array, this is the worst case, and a valid case in between. Okay. This is chapter 3. Okay, I'm going through these chapters because most of you makes here. Let me go to chapter 4, then we go to here. Recursive algorithm. Break problem into smaller version of itself. Generally, case recursive version in which smaller version of itself is called must eventually be reduced to base case. Basically, you can think a recursive method having unlimited copies of itself and calling its own code, set of parameters and set of local variables. If the problem can be solved for n, solve it. Else, recursively call apply the algorithm to one or more problems involving smaller values of n. Combine the solution to smaller problems to get the solution of the original. Here we have example. Here 24, 88, 40, 37. A list can be defined recursively. A list is a number or a number comma list. So list number number list. So here this is a basic recursive representation of this list. 24, 88, 40, 37. So here have 24, here 88. So you have 40, 37, number of, here we have 88, comma, here we have 40, 37, we have number 30, comma, here we have 37, number, here we have number 37. This is example of recursive. So here we have example, consider the problem of computing sum of all numbers between 1 and n. Like factorial, here we have summation. The base case is 1, means if n equal 1, return 1, otherwise we make plus. This problem can be expressed recursively as sum of n is n plus f n minus 1 recursion of combination. So here we have public sum here. This is the n equal, if n equal, return minus 1 plus if n equal 1, result equal 1, else return n plus some integer n minus 1. This is a recursion for calling the sum integer. So method returns, method invocations, they mean some integers. Here some integer 4, some integer 3, some integer 2, some integer 1. So here we have start with 1, then here we have 2 plus, here we have the result of, because here we have, this is some integer. So here we have result 1, here we have n, because here we have n plus n minus 1. So here we have 2 plus some integer 2 minus 1 here. Here we have 2, here we have 3, we have 4, we have 5. Here we have n. So we have 5, some integer 5 plus minus 1. Then we have 4, some integer 4 minus 1. Then 3, some integer 3 minus 1. Then here 2, some integer 2 minus 1, here 1. Then we have now replace 1, here we have some integer 2 minus 1, equal 1. What is here? You have, we have written 1. So here we have 3. 1 plus 1, here we have 3 minus 1, 2, here we have 3. We have here 3 plus 3, 6. So here 4 minus 1, we retain 6. Here we have 6, 4, 10. Here we have 10, here we have 5 plus 10, here 15. Example of factorial. What is factorial? Mathematical function where fn, here the factorial number, n factorial 1, here otherwise n times n minus 1 factorial. Public static n factorial n, if n equals 0, retain 1, else retain n factorial n minus 1. N times factorial n minus 1. Recursive steps, here we have n fact value while n less than equal 1, fact value times n minus minus, retain fact value. Okay. This one factorial. Previous year was summation. This one is factorial. Okay, Fibonacci, we did Fibonacci 0, 1, fn n minus 1, fn n minus 2. And this also we have a discussion of this one in one of the project of your friends last yesterday. We go through this example of Fibonacci. So we have to repeat the Fibonacci again, the problem of Fibonacci. Plan of analysis of regression algorithm, decide on parameter indicating the input size. Here, how to analyze. Decide on a parameter indicating an input size. Define the algorithm basic operation. 6. Whether the number of times the basic operation is executed may vary on different inputs of the same size. If it may be the worst average, the best case must be investigated separately. Set up a recurrence relation with an appropriate initial condition reducing the number of times the basic operation executed. Solve the recurrence, or at the very least establish its solution order of growth by backward substitution or another method. Here we have what is recurrence relation. Many arithmetic functions can be expressed as recurrence relation. N power 2 can be expressed as recurrence relation. N equal an minus 1 plus 2 times n minus 1, where a1 equal 1, a0 equal 0. Here we have equal fn minus 1. Here equal to n minus 1 to n minus 1. We have fn minus 1 times plus 2n minus 1. A recurrence relation is an equation that regressively defines a sequence of multi-dimensional array of values. Once one or more sequential terms are given, each further term of the sequence of array is defined as a function of the preceding terms. Okay, here examples. Fn minus 1, f minus 2 for Fibonacci. Here, most methods solve recurrence. Here, non-universal methods to enable us to solve every recurrence relation. There is several techniques. However, some are powerful than others that can solve variety of recurrence. Method of forward substitution and method of backward substitution. Starting with initial terms or terms of the equation given by initial condition, we can use the recurrence equation to generate the few first terms of the solution in the hopes of seeing a pattern that can be expressed by a closed-end formula. So, for example, consider the recurrence xn to x minus 1 plus 1 for n greater than 1, x1 equal 1. Most of you solved some of the question wrong, this one. So you have method of forward substitution. We have here 2 n minus 1 plus 1 for n minus 1. We replace n with 1. So here we have x1 equal 1. We return the few first items as follows. Here 1, 2 plus 1, 2 times 1 plus 1, 2 times 2. Here we have this one. This one we call it forward substitution. It is not difficult to notice that the number of are on less than the consecutive powers of 2. So here we have xn, 2n, 2 power n minus 1 for n 1, 2, 3, 4. We can prove the hypothesis that this formula yields the generic intent of the solution b.5 and b.6. So here we have either by directly substitution of the formula into b5 and b6 or by mathematical induction. Here we have this example for forward substitution. We have backward substitution. That is method solving recurrence relation works exactly as its name implies, using the recurrence relation in this question. We express xn minus 1 as function of x minus 2 and substitute the results into the results equation to get xn as a function of xn minus 2. So this is here xn minus 1 is plus n, x0 equals 0. As an example, let's apply a method of backward substitution recurrence b1, b2.